Good morning, Shubham Injane. After this work of Gauss law and applications, now let us do some examples based on electric flux and Gauss law, the intensities. Today we'll do some simple examples. Remember, simplification, last 2-3 times also what I found is that I forget some things, multiplications, divisions. Make sure you don't do it, and if anything such simple things I have missed, make sure. Even I try to make sure this time onwards we don't miss anything regarding calculations, right? See, this example is electric field is given. An electric field 3I plus 4J into 10 cube Newton per Coulomb given in SI units present in a region of space, right? Find number of field lines through a planar surface of 80 centimeters square. 80 centimeters square held in y-x, this is xz plane, held in xz plane. Now when you look at this entire data, vector notation is given, E bar is given, and he says number of field lines. You know the number of field lines? Nothing but flux. Is it not? Number of field lines? Nothing but flux. Now the surface is given in the scalar form, but remember its orientation is given. Therefore now when you read the entire data, we have to use the definition of flux to find the number of field lines. What is the definition of flux? Phi is equal to E bar dot A bar, a dot product of vectors. Now in this, when I write the data says E bar value is, magnitude is given 3I plus 4J times 10 cube, right? Of course this is in SI units, Newton per Coulomb. The other unit also I have told you, right? Volt per meter, like this. Now this is E bar. Now what is A bar? A is equal to 80, look here, it is centimeter square. Therefore this is 80 into 10 raised minus 4 meters square. So all the things in SI units. This should be a kind of like default mandatory. Never say that you have forgotten. 80 into 10 raised minus 4 meters square. If this is what is in, and he says it is in XZ plane, right? In XZ plane. Now what is our definition of A cap? Remember, the surface area is always an outward normal. Therefore, that is what is mentioned. Since A cap is always an outward normal. Now for XZ, which is the normal. For XZ plane, the normal is y-axis. Y-axis means J cap. Because of orthogonal unit vectors, remember, X direction means I cap, Y direction Z cap, Z direction K cap. So this is our representation of a given direction in the orthogonal Cartesian system. So outward normal. Therefore, now this A bar is equal to, this is 8 into 10 raised minus 3 J cap. Why J cap? Why J cap? Perpendicular to XZ means it is y-axis. Therefore, this is 8 into 10 power minus 3 J cap. Of course, the unit is there, meter square. So this is the only thing from the data which is in the scalar we have converted that into a vector, right? Vector form we have converted. Therefore now our definition phi. Please don't write phi bar. It is only phi the scalar. Phi is equal to E bar dot A bar is the number of field lines passing through the given surface, and the number of field lines is nothing but the flux. So phi is equal to E bar dot A bar. So it's now finally left with your data. That is 3I plus 4J, 3I plus 4J, and the dot is this one. Dot is 8J. Now all other multiples, submultiples. This is 10 cube and this is 10 by minus 3. This is 10 cube you see here, and this is 10 by minus 3, and that will nullify. Is it done? So simply now it will be 3i plus 4j dot 8j. So this is nothing but 8 3s are 32. So this is what is 32. Suppose if you have to write the unit for flux, if it is for unit for flux, of course you know that it has old meter. Is it not? Old meter is the SI unit of flux. And now simply it says ask the number of free lines. So the number of free lines is 32 through the given area. Like that. Is that okay? So whenever it is asked either flux or free lines, we are finding this definition, or sometimes we may use that Gaussian expression, integral E bar dot ds bar. And one more time, supposing in the same example I have a small change. Here field is given and asked, is it not? And further to have given this solution. Look at it. Now I simply change the data. In the data I say a charge magnitude and a kind of geometry I will give, and again ask you to find the number of free lines. Question is like this. If a charge of 3 micro Coulomb, if nothing is mentioned, I will take it as a positive charge, right? Positive charge, what will be getting? Outward flux you will get, negative charge, inward flux you will get, right? If a charge of 3 micro Coulomb is placed at the center, supposing I said at the center of a cube, of edge 25 centimeter, the edge of the cube is given to be 25 centimeter. Now the question is, find the number of field lines. See, these are very simple examples for our board exam. Find the number of field lines through one of the faces of the cube. One of the faces of the cube. Right? The data says the given geometry is a kind of cube. A cube of edge 25 centimeter. We know that what is that cube? Cube with 12 edges. Remember? Cube has 12 edges. Cube is a 3D geometry. It has 12 edges. The given charge at the center of the cube. At the center of the cube. Right? Therefore, if I take, this is what is our cube. This is the cube. This is the center of the cube. Right? Supposing if I give the naming A, B, C, D, E, F, G, H. So these are the 8 corners, 6 faces. You can now find such details about any geometry you should be knowing, right? Now what about this geometry? It has 12 edges. Edge means this one. This is what is called as one edge. That is what is, they become 12 edges, 6 faces. Is it not? Now here this is the charge placed cube. This example we are doing in the simplest case for our board examination. The same example can be given with the orientation of the cube, axis, different directions, right? Asking for the flux. Then we should make use of the same concept of IJK. But now here I simply said that this is a cube. Q is given to be 3 micro Coulomb, of course. And this is what is the edge given to be 25 centimeter. So in the given data, Q is 3 micro 3 into 10 raised minus 6 coulombs, right? This much, and the given edge is there. Remember what we have told. The flux to any closed surface depends only on the net charge and of course the medium, but does not depend upon the shape or size of the enclosure. You remember? So I will make a mention, even in the board examination also, this is what is the superiority shown by the student, the metal shown by the student. Now I am writing here the flux through closed surface. Flux through closed surface is independent of its size or shape. Even shape also doesn't matter. Size and shape doesn't matter here. Is it not? Therefore now, and flux enclosed is nothing but phi is equal to Q by epsilon naught, which is our Gauss law. Earlier we have used that E bar dot A bar, the definition of flux. Now this is what is Gauss law, flux. If Q is the net charge, you remember this is what is Qi, the net charge enclosed by the surface by epsilon naught. Now remember, he has asked for number of field lines. In the very beginning you will write, what is that? In the very beginning you will write, the number of field lines is nothing but, number of field lines is nothing but flux. Is nothing but flux. That is what we are calculating, flux. Now this phi is equal to Qi by epsilon naught for the entire cube. Entire cube means, as I have told you, this cube has how many faces? Right? 6 faces. So this is what is phi is equal to Qi by epsilon naught for 6 faces. For 6 faces. Now we are asked to find through one such phase. Remember here the question is, yes, the number of field lines through one of the faces of the cube. One of the faces, here I take how many 6 faces? One such face I am showing here, A, B, H, E, one such face or any other face. It becomes 1/6 of this value. Therefore, our lost line is the flux through one of the face. Right. Flux through 6 faces. 6 faces is Q by epsilon naught. Hence, through one of the faces. Through one of the faces is 1/6 times Q by epsilon naught. So this is our answer. And of course, you know the value of epsilon naught also, because we have already used it while introducing in Coulombic force. 8.8 into 10 raised minus 12, 8.85 into 10 raised minus 12 if you want that second digit as well. Therefore this is 1/6 times. This is 3 into 10 raised minus 6 and epsilon naught value 8.8. I take only one decimal and this is 10 raised minus 12. So whatever number that you get, you will have it. While having that number, I will give you one simple suggestion for you. What is that? This is 10 raised 6 it becomes, is it not? This is this numerator is 3 and denominator is something bigger number you are getting. Therefore, what I ask you is, so you better make it as 300. If you make it as 300 and you will make this as 6 8 48. 6 8 48 and this is 50, 6 5 68. So one decimal I have taken here. One decimal I have taken, this is minus 13 and minus 6 plus 7. 7 I have taken 2. Therefore this is 10 raised 5. This is 10 raised 5. Like that. Okay. Now you can do this number. This is 568, 300, whatever. Now it will be your case that you will do. So multiple submultiples whenever is there, you try to have a convenient one numerator. Suppose even if you make it as some 3000, then it becomes 3 rise 4 like that. Don't remember here this 160 because it is asked you to calculate through one of the phases like that. Now here remember what is the position of this charge. Is it not? Position of this charge. It doesn't matter inside, it can be placed anywhere, answer is the same. Need not be at the center, somewhere over here, this and all, it will be the same. But sometimes there can be a change, an interesting change that we will discuss in our coaching classes. Let us not do that here. Exactly supposing if it is placed at the corner, exactly at the corner, or else it is exactly placed at the one of the faces, something like this. All such examples will do upwards. So this is the case of finding flux into some examples that I have shown, right? Now let us see the one more example. In that example, I am calculating in case of electric field. This example says tiny oil drop is charged. It is a charged oil drop, and oil drop will consider it as a conducting material, right? Remember, I will treat it as a conducting. A tiny oil drop is charged such that it causes a maximum electric field of 750 volt per meter. Here the unit is given to be volt per meter. We can use either Newton per Coulomb or volt per meter, I have told in the beginning. Now it is said that if it is split into, that oil drop is split into 125 identical small droplets. 125 number droplets, find field due to each smaller droplet is the question. Now here it is nothing but I'm writing the expression for the electric field intensity due to a conducting sphere, charged conducting sphere, whatever cases that we have discussed. Here the important point is maximum electric field. Maximum electric field always in the case of charged conducting spheres, that maximum always refers, yes, on the surface. On the surface in the case of conducting material, I have told you, right? So it is now, see, to begin with oil drop, we are always, since it is a tiny oil drop, effect of gravity is negligible. Therefore, we always take the case of the effect of surface tension. Therefore, they are all spherical in shape to begin with. Remember, all these oil drops under consideration, whether it is bigger drop or smaller drop that we have taken relative sense. The tiny drop and then each smaller drop, all are considered to be spherical in shape. Therefore, now here I am writing for bigger drop. I am writing for bigger drop. See, this is the simple case I am showing you. If this is what is the radius, capital R, and the charge is capital Q. Now I will write it as E bigger. E bigger is equal to K capital Q by capital R square is for the case of bigger. I am writing B for bigger, or you write bigger. E bigger is equal to KQ by capital R square. Look here for the symbols capital Q and capital R. Now what it is done, it is said that they are into large number of R125. Some number is given, I call it some N. These are identical 125, identical number is also, identical statement is also there, 125 identical. Then I am now taking for smaller drop, each smaller drop I am taking, right? Each smaller drop I will call it as charge is equal to small q, and radius is small r. So these are the things. For the bigger one we had taken capital Q for charge and capital R for radius. Here small q for the charge and small r for the radius. Now in the case of charge it is additive property. Since it is cut into n equal parts, right? Since bigger, since bigger is split into n identical drops, smaller drops, then what happens? This small q is equal to yes, q by n, 1 by n times. Is that okay? This is 1 by n times of 1 by n times of capital Q. Why? Additive property, is it not? If 10 units is divided into 10 equal, 10 identical, then it should be 1 each, right? So here this is what is 1 by n of capital Q. Now what about this small r? We have to relate the small r also in terms of capital R. Now remember, when a bigger one is split into smaller ones, what happens? Some parameters will have a change, like radius of bigger drop, radius of smaller drop, surface area of a smaller drop, surface area of bigger drops, total surface area. All these things will undergo a change, but one thing remains constant. What is that? The volume remains constant. Supposing if I have 1 liter of liquid, and all that 1 liter of liquid, if I poured it into some 20 or 30 different small vessels, then many things are changing, but one thing is remain constant. What is that? Yes, the total volume. When you mix all those again 20 vessels, you will get a same 1 liter. So in this case also, the splitting or opposite to this, smaller drops when they are merged to form a bigger drop. In such case also, in all such cases, the thing which remains constant is the volume, and hence of course we can also call it as a mass bounding with a condition that temperature remains constant and all. Therefore here the volume remains constant. Therefore now I will make use of such condition to find a relation between small r and capital R. Therefore now what I am writing is the condition volume of total volume, I will write, right? Total volume of n drops is equal to volume of bigger drop. Is that okay? And now equating the volumes. Right. Therefore, what is the volume? As I have told you, here all are perfectly spherical geometry that we are taking, right? Therefore, this is the volume of a sphere, 4/3 pi capital R cube for, okay, small r cube if I write. This is small r cube if I write. This is for each smaller drop, and it is said that how many number, n number are there. Therefore, n times 4/3 pi r cube is volume of the bigger drop is 4/3 pi capital R cube. Now a small simplification, you will do that, right? What is that 4/3 pi? You have seen. Therefore, small r is equal to capital R by n rise 1 by 3. Cube root is there, right? Cube is there on either side. Take the cube root. R is equal to capital R by n power 1 by 3. When you do such things in one example, remember these are some regular things. In any other topic, whenever you come across such splittings, identical, here we did it identical, and the result between capital R and small r, like that, right? So small r equal to you got. Therefore now I am writing for each smaller drop. Let us write an expression. Each smaller drop, E small is equal to the same expression, K Q by R square. Is it okay? Is it okay? If now I will take this ratio, I will take, right? E small expression, E small is equal to K small Q by small R square. Now I am writing E small by E big. Take the ratio. This K is a common term, right? That's good. Therefore, this is nothing but small q by capital Q. And then what is that? Capital R by small r. Capital R by small r. And this is a square term. This is a square term. So you got the answer right? Now a further simplification, in fact, please you have to do it that this Q by capital Q, you will get it as 1 by M, right? 1 by M. Capital R by small r, you will get it as capital R by small r, you will get it as n power 1 by 3. Therefore, this is n rise 2 by 3. You get square term is there. This is n and this is n rise 2 by 3. All those simple things. Therefore, this is E small by E big. What is that you got? Yes. 1 rise n power 1 by 3. This is n. This is n rise 2 rise, right? N rise 1 by 3. Therefore now E small is E big is given. E big is given to be some number I have given. You remember I have given I think some 500, 750 I have given. 750 by n value given to be I think 125 I have given. So this is 125. Whole rise 1 by 3. 125 whole is 1 by 3 is 5 value, right? So 750 by 5. So that is nothing but 750. Yes, 150. 750 by 15 number. Whatever number comes, you will do it. So that is what is the answer. This is what is the 50 volt per meter you will get. Now here, these things when you practice, don't try to memorize this. E small by E big equal to 1 by n power 1 by 3. Because of a couple of days or weeks, is it 1 by n power 1 by 3 or n raised 2 by 3? All such things will come. So as much as possible have a logic, because here the relation between small r and capital R is the key one. If you remember this one, any other example when you are doing it for competitive examination, time is not a problem. But don't try to memorize this kind of expressions, right? Shortcut somebody says, or long cut somebody says. Memory always gives you stress. So in the physics, the funda is less memory, more logic. Right. Let us see one more example. Friends, remember, last example we had a result. What was the result? You remember? E small is 1 rise. 1 upon n is 1 by 3 times. E big was our result. This is with respect to capital E, right? Now the same can be another result you can write, identical result you can write with respect to surface charge density. Why? Because remember we have done this relation for the case of a spherical charge conductor. Spherical charge conductor, E is equal to, right, sigma times epsilon naught, sigma upon epsilon naught, right? Sigma upon epsilon naught was our result. Here epsilon naught is a constant, therefore sigma proportional to E or E proportional to sigma is a one important result. I hope you remember we have done this expression. Therefore, the same expression now, our identity is sigma proportional to E, or vice versa. Anyway, E proportional to sigma, sigma proportional to E. This is our result. Therefore, the same we can write it as sigma small is equal to 1 upon n plus 1 by 3. Sigma big is also the same result. It's also same result. Okay? In fact, earlier example we had told bigger drops split into smaller drops. Even it can be in the other case, identical charge drops merged to form a bigger drop. And that is why most of the students, when they memorize they always try to memorize a formula such that they know only one way what is to be calculated for given right hand side, we will calculate left hand side. That is how people try to, and that makes a big difference, I am telling you. Even if a small change is made, then the students will find it as a very, very big difficulty. And that is why look at this as a concept, what is done. Therefore, if it is said to be unified, merged, right? In such cases, E small is given and you will find as E big. Or E small is given, E big is given, how many such number is there, anything can be asked, because any expression when you look at 1, 2, 3, 3 terms are there and 3 terms are related with a simple mathematical expression. What type of relation is there, which is the known quantity, which is the unknown quantity, what better changes can be made in that. So it is how you will look at it as a complete package. Whenever I do one solution or one concept, after that I have told you many times, if my job, if I did my duty for about 1 hour, it will be another 2 hours duty or responsibility from your side. Don't forget that. I keep repeating these things time and again, so that at least I definitely can find those 20, 25, right? Who makes a very purposeful journey with us. This example, copper sphere, radius 3 cm, placed in a medium of dielectric strength, a new parameter, new term that you have observed here, placed in a medium of dielectric strength 45 to 10 raised 3 volt per centimeter. Find maximum charge that the sphere can hold is the question. Now here, this dielectric strength can be a 1 mark, 2 mark question for you as well. Right? First let us define what is the dielectric strength. This dielectric, what is that? Insulating materials, insulators, what we call as dielectrics. So dielectric constant, dielectric strength. Dielectric strength. What is meant by insulator? We have already given the characteristics of insulator. Conductor and insulator. Conductor will cause the flow of charges, of free charges. Insulator unable to do that. So the so-called insulator will not be insulated forever. What does it mean? A material which is said to be a dielectric or an insulator will have its insulating properties only up to a limit. In some extraordinary conditions, if limit is crossed, then the dielectric, the insulator, starts working as a conductor. So that is what is the meaning of dielectric strength here. Now when we said that limit, what is that limit? Now we define. So dielectric strength, it is the maximum. It is the maximum electric field. It is the maximum electric field that a dielectric can withstand without losing its insulating properties, insulating characters. Means in the brackets I make one more mention. Beyond this limit, the dielectric works as a conductor. So beyond this limit, yes, dielectric works as a conductor, as conductor. So that's what is the meaning of dielectric strength. It can be a 1 mark, 2 mark question, remember. Therefore now, let us come to our question. What is the data given to be? The radius is given. The radius is 3 centimeter. 3 centimeter, and all the data always in SI units. Radius 3 centimeter. Now, we know that E maximum, which is nothing but dielectric strength. E maximum is nothing but dielectric strength, and E maximum is equal to ES for sphere, conducting sphere, E maximum is equal to ES. If now, if I combine these two results, what is that? ES is equal to dielectric strength is given to be, look here, one more time look at that 45 into 10 rise, 3 is given, right? And here is volt per centimeter. What is the SI unit? That is what another small thing that I have made here. Always whenever you are substituting for these magnitudes, please make sure they are in SI unit. Volt per meter is the SI unit. Here it is volt per centimeter is given. Per centimeter when converted into per meter, the factor is 10 square. Because centimeter if you convert it into meter, it is 10 raised minus 2. Per centimeter converted into per meter, therefore it is 45 into 10 raised 5. So 45 into 10 raised 5 in the SI units. And that is why every time whenever I give you an example, what I would like to see that they are given in some other different units and you try to, you always not try, you first you have to convert them into SI units. So it is 45 into 10 raised 5. And what is ES? We know that this is what is KQ by capital R square is equal to 45 into 10 raised 5. And of course all the values are known, you will get the value of Q. K value you know, 9 into 10 raised 9. We have been using it since our Coulomb's law, right? Radius is given, all converted into SI units, therefore now it is only the case of, so this is 9 into 10 raised 9 Q by R squared is also 9 into 10 raised 4 equal to 45 into 10 raised 5. So this is Q is equal to this is 13 and this is 8. Therefore this is 45 into 10 raised minus 8. Or else I can write it as 450 if I write it as nano coulomb, because 10 is minus 8. Generally our standard submultiples that are used are milli 10 power minus 3, micro 10 raised minus 6, nano 10 raised minus 10, pico 10 raised minus 12. These are our regular, that is why I have taken a 450 nano coulomb is what is Q maximum. This is what is Q maximum that the sphere can hold. We got our answer. Now the question comes, maybe rationed out to some of you may have this. Supposing if we give more than 450 nanocoulomb, what happens? Is it not? Supposing it doesn't take, it doesn't hold. Therefore, whatever excess is there, that excess will be given away to the surrounding medium. Such flow of charges from the conductor to the surrounding medium is what is called as, yes, you keep looking at many times, that is what is called a spark. There is a spark, somebody will call it, right? What is meant by spark? So from conductor to the surrounding medium, the charge flows. Why the charge flows? Because of this kind of exceeding, the field exceeding that dielectric strength, conductor will omit the charges to the surrounding medium. That is what is called a spark. So this is one example where one important definition. And one more time I have shown that volt per centimeter is given. If I will have converted volt per meter, then making use of our simple expression, right? And this is what is ES value. One more example, we'll continue. AB or concentric shells. Place one inside the other. Place inside the other. A is a bigger shell, or supposing I say this is what is A, the bigger shell is B, right? So they are concentric shells and both are charged such that A has a charge of minus 3 microcoulomb and B has a charge of positive charge is going to be 5 microcoulomb. The radius of this inertial is going to be 5 centimeter. That of the bigger sphere B is going to be 10 centimeter. These are the radii of capital A and B, the bigger small shells. Now here it is given with 3 different locations. What is that? the point P1, P2 and P3 such that the distances of these from the center is given. OP1 is equal to 3 centimeter, or OP2 is equal to 6 centimeter, like that. OP3 is given to be 15 centimeter. So this is what is the entire data. And now it is said that find the intensity at the sites of P1, P2 and P3. Find the intensity is our question, right? These are concentric shells, a shell inside another shell. Now, we know that at any given point the intensity will be the vector sum of the different possible intensities at that particular point. Intensity always defined at a point, number one, and number two, at any given point the intensity is the vector sum of different possible electric fields at that point due to different sources. This is our concept, right? Therefore, whenever we wish to find intensity at a given point, observation is very important. What are the different possible sources to produce electric field at that particular point, right? Then individual intensities. After that, of course, we have the principle of superposition, vector sum. Now, supposing if I said at P1, look at the position, the site of P1. P1 is inside the inner shell. Therefore, this happens to be at P1. If I said P1 is inside point, yes, with respect to both A and B, the smaller shell A and the bigger shell B, with respect to both of them, it is an inside. And what is our principle? What is that the result that we have deduced in the previous sessions? Any inside point, in the case of a shell, any inside point field is 0 for the reason that the net charge is 0, is it? Including center or any inside point. Therefore, that is what now mentioned here. So, by principle, at any inside point, field is 0. Field is 0. Therefore, I will make a mention of with clarity. What is that? EI due to A is 0. EI due to B is also 0. Therefore, E at P1 is equal to 0. Is that clear? Therefore, next time, even if the point changes, then for you writing that and making that will be easier. Of course, in the given example, you can see that there are positive and negative charges, right? Positive and negative charges when given, what significance we will see. Now let me write at P2. Now look at that point P2. P2 is an outside point with respect to A, whereas inside point with respect to B. That I will mention. At P2, I am writing P2 is an outside point. P2 is an outside point. Yes, it is with respect to A. Such that what is the distance of P2 from the center? It is also given to be 6 centimeter with respect to A. Therefore, now what is E due to EO due to A is equal to, our definition is that K Q of A by R square, where this R at a distance, I will here mention at a distance R is equal to 6 centimeter according to the data. Therefore, this is EO due to A is equal to KQA by R square. Substitutions will give you the number. This is 9 times 10 raised 9, 1 by 4 per epsilon naught value. QA is going to be 3 microcoulomb. Field examples. No sign carried into the simplifications. Have told you earlier also, right? Therefore, this is simply 3 into 10 raised minus 6, right, microcoulomb. And the distance is 6 centimeter. Therefore, this is 36 into 10 raised minus 4. This is 6 into 10 minus 2. All these things, of course, right? So this is 4, 3 by 4, 3 by 4, and this is like yes, got it. This is 14. So this is 3 by 4 times 10 rise 7. 10 rise 7. This is of course unit, you can write it as volt per meter or Newton per Coulomb in each of your choice, 0.75, or this is 7.5 into 10 rise 6. Is that okay? 3 by 4, 7.5 into 10 rise 6. You will get the value in mega or million. This is the unit will be volt per meter, of course. Now whereas again I am writing you P2 is yes an inside point. P2 is an inside point with respect to B. With respect to B, therefore E I due to B is equal to 0 at P2. So B shell is, or the charge on the shell be not contributing, or the intensity is intensity due to B at P2 is 0, is what is the point. Therefore now E at P2 is simply 7.5 into 10 raised 6 volt per meter. Volt per meter. Now if I have to show the flux is 0 inside this, inside A, no flux is present. Whereas between the shells A and B, in this space, there is flux and there is field. What flux is there? Since this is a negative charge, yes, now the flux you will show, this is what is inward flux. Inward flux at A you will find, at the surface of A, what you find is, this is what is the inward flux that you observe. Right? Now the same will continue for P3 also. Now look at that P3. P3 is a point which is an outside point with respect to both A and also B. Right? Suppose if I am writing at P3, yes, P3 is an outside point with respect to both A and B. A and B, such that here you see one important thing. Here you see one very important thing. Such that R is equal to OP3 is 15 centimeter. R is equal to 15 centimeter. Yes, with respect to both A and B. Now, what is the distance of the point P3 from the center of A or from the center of the B? It is with respect to both A and B 15 centimeter only. 15 centimeter only. Now let us use our Gaussian surface and expression. Now let us not write both E1 and E2 because that will give a confusion for you. Instead, let us use our Gauss law for this outside point. So for outside point, what we are doing is, yes, outside point using Gauss law. Using Gauss's law, right? Using Gauss's law, integral E ds cos 0 degrees. Because this we already did it, right? Shells or charged conducting spheres or non-conducting spheres is equal to, yes, sigma qi by epsilon naught. Sigma di by epsilon naught. Then this E is a constant because it is a symmetric geometry, equidistant from this, right? Therefore, E times 4 pi r square is equal to, yes, sigma qi by epsilon naught. Therefore, this E is equal to, yes, now you got this expression as 1 by 4 pi epsilon naught. What is the sigma qi? Sigma qi is 5 minus 3 into 10 raised 6. Right. So now you got your answer. 5 minus 3 into 10 raised minus 6. This value you know. This is what is E at P3. Like that. Is it okay? Concentric shells we told, and what about the flux outside? Outside, what type of flux will observe? At least such smaller things I will leave it as a small work for yourself. Try to do it, whether you get outward flux or inward flux, and why. According to your understanding, try to do that, and for any clarity, you are at liberty to call your teacher, right? So with these examples, I want to end this session. Tomorrow's session, I will see that you will get a good number of examples through your college group. You will get good number of examples. Solve them. For any of the doubts, you can call your teacher. Next session will start another very big and interesting topic. Till then, good day. Eat well, prepare well. Good day, boys.